Right, so since we're a little bit late, let me welcome Professor Perdikaris from UPenn, our first CICS seminar speaker for the spring. I noticed there is some small changes on his title. He will speak on probabilistic data fusion and physics-informed machine learning.
All right, thank you very much, Nicholas. Can everybody hear me? All right, all good? Well, that's a big room. So yeah, thank you very much for the introduction and the invitation. Had a great day so far, so happy to be here. So today, my focus will be on presenting some recent work at the interface of scientific computing and machine learning. So let me start with some motivating remarks and some sort of high-level applications. We're not going to see many applications today. My motivation is mainly on the methods development, but hopefully that will spark some interest for discussion. All right, so the big goal, the big picture is that we want to model, analyze, and perhaps optimize complex systems, and these come in many flavors. And you can see sort of like two extremes here on the screen that define sort of different fields these days. So you may have systems and applications for which we have a lot of data. We have streams of online data collected, but we may not have a lot of modeling knowledge. Say on the left you have this autonomous car driving around the streets. There's a lot of information input from GPS and LiDARs and cameras and sensors and so forth, multi-model type of information. But there's not many models really. We don't really have models to predict how fellow drivers drive or pedestrians walk. So we have to make decisions in a system like this purely based on sensory input and data. While on the right you have another system that we can analyze using first physical principles. That's, modeling flow past an airplane wing. We know conservation of mass and momentum in fluids. We can nowadays use large supercomputers to simulate a system like that and gain some predictive understanding. So essentially, this defines the spectrum between, data applications in which data is dominant, or applications in which we may not have a lot of data because data acquisition is very high. It may involve expensive experiments or very expensive supercomputer simulations, but we do have a lot of prior modeling knowledge available. So those two extremes these days are defining two fields. Now on the right you have CSE, which stands for computational science and engineering, while on the left we all know the huge success of the field of machine learning is enjoying these days. So the motivation is to develop methods that essentially allow you to seamlessly slide through this one-dimensional spectrum between data and models. But of course, there are several challenges that need to be addressed along the way. So challenge number one would be the high cost of data acquisition. In many, many applications, we have complex systems that are prohibitively costly to probe, or perhaps the quantities that we're interested in are hard to measure. Therefore, we may only have access to limited and perhaps high-dimensional data. And by high-dimensional, I mean things like images or time series that you may have thousands or millions of entries per data point. You may have multiple modalities, large parameter spaces to explore, especially in the context of design or sensitivity analysis. So, for example, the airplane wing, it's defined by a set of tens to hundreds of free parameters. If you think about optimizing the shape, you have to navigate this large parameter space. You may have to deal with cases that include missing data or outliers, or whatever you measure may be corrupted by complex noise processes. That's very relevant to the experimental setting. And of course, you want to do predictions with quantified uncertainty, especially if you care about downstream tasks like design and control. And of course, central to these topics is the role of surrogate models, and by that I mean models that can serve as a proxy of the real system. So our goal for this talk, and you'll see the talk will be mainly focused on how can we learn functions from data and how can we learn probability distributions. And these are the main tools that allow us to model input-output relationships that allow us to build, in return, surrogate models which we can then sample cheaply. So if we do know the relation, how inputs relate to outputs, then perhaps we can avoid running these very expensive simulations or acquire more expensive data. And the hypothesis here, of course, there's many techniques, and methods for learning functions from data or probability distributions. The hypothesis of this talk is how can we leverage recent developments in probabilistic deep learning to try to tackle, to some extent, some of these challenges that I list there. All right? Okay, so the talk will be primarily focused on building surrogate models. And in the next slide, I have some advantages and limitations of perhaps some of the most prevalent, okay, they have the outline of this talk. So the outline of this talk will be split in two parts. So part number one, I'll talk about data-driven surrogates. In that setting, we will assume that the data generating process, generating from input going to output, will be a black box, and we will just try to recover a function or probability distribution out of it using conditional generative models and latent variables. While in the second part of the talk, the data generating process will no longer be considered as a black box. It will be more of a colored box, as you see there. It might be an arbitrarily complex colored box like this Jackson Pollock painting, which means that we may have some underlying physical knowledge about the system, typically in the form of knowing an evolution law described by partial differential equations. All right? Okay, so let's go back to probabilistic surrogates, and perhaps in the nonlinear setting of approximating nonlinear functions with nonlinear models, these are perhaps two of the most popular approaches these days, namely Gaussian processes and Bayesian neural networks. And here's a list of some pros and cons of those two approaches. So let's see first Gaussian processes. They do have an elegant mathematical background. You can derive things and you can prove some things about their properties, their convergence, and so forth. They are quite flexible models in encoding linear constraints, thanks to the remarkable property of Gaussians that they're closed under linear transformations. They're robust in small data regimes, and they give robust uncertainty estimates in practice. And they are a Bayesian model in nature, so they have built-in capabilities for uncertainty quantification that enables downstream tasks like experimental design or active learning, active data acquisition. So these uncertainty estimates can guide us on resolving the problem and acquiring more data. On the downside, they may have some limited expressivity because the user has to choose a kernel or a prior. And there comes the question of kernel design. For a particular problem, we have to make careful choices there. Unfortunately, they're not scalable to large data sets. So exact inference in Gaussian processes has a cubic scaling of the total number of data points. And of course, the robustness with respect to those prior assumptions is also an important topic. On the other hand, Bayesian neural networks address some of those limitations. They're very flexible function approximators. They can easily scale to high dimensional, well, easily. Well, if the data has a particular structure, like images or time series, they can scale to high dimensions. They can easily scale to large data sets. And they're flexible in encoding. They're differential representations, so it's flexible to take derivatives of neural networks, as we'll see later, and encode algebraic and differential constraints. But on the downside, if you think of casting them in a probabilistic setting, they are governed by complex and high-dimensional posteriors that they're quite hard to approximate. You cannot perform exact inference in these models. It's hard to get robust and meaningful uncertainty estimates. It's hard to ensure robustness in small data regime and avoid things like overfitting. And of course, finally, the interpretability of such models. All right, so let me start with the first part of the talk, which is motivated on constructing probabilistic latent variable models. So in this setting, we want to construct a model that can approximate conditional probability densities, like what you see here in the slide. We have inputs x, outputs y, and we want to make a statement about the probability of y given x. And the way we'll set up the problem here is by making the following assumption. So here you see on the left, you see those points in the physical space. These are paired observations of inputs and outputs. We will make the assumption that every single data point in this physical space is generated by some nonlinear transformation, f theta, of the inputs and a set of latent variables z. All right? Where you see on the left here the latent space with two components, z1 and z2. So essentially, we'll assume that the outputs is equal to f theta of x and z, where z comes out of some prior distribution that we choose. And we'll try to train a model based on the data to approximate this conditional density. Now you can compare this observation model that you see on the top with what I just plotted in the bottom, right? You can think of this as a generalization to the standard observation model people use in regression, namely y equals f of x plus epsilon. This is a simple additive model. We typically assume it to be epsilon as a zero mean isotropic Gaussian. So this latent variable model that I'm listing there can be thought of as a more complicated, more general way of modeling noisy data, perhaps, or stochastic data. And then the standard regression model is just a simple subcase, as we will see. All right. By the way, if you have any questions at any point, or if I'm going too fast, please feel free to interrupt and ask any questions. Of course, now the question is, we have postulating a model like this, and here's some basic rules of probability of how this conditional density looks like. But in practice, how do we train it? Someone gives us a cloud of pairs of input and output pairs, and we want to fit a model parameterized by some parameters theta to approximate this conditional density. So how do we do so? There's many different ways of doing it. These integrals are not tractable, so for any reasonably interesting model for f theta, namely any nonlinear model, we cannot really perform any exact inference here, so we have to make approximations. And throughout this talk, we'll use approximation tools from variational inference. And in particular, we will try to train this model on data by matching the joint distribution of the model. So we have a generative model, p theta, that generates, given an input x, can generate samples y. And how this is done is shown by this formula. So given an input x, we can sample a z out of the prior and push those two inputs through this nonlinear function f and get a sample for y. So this is how the generative model works. And we'll try to minimize, in a probabilistic sense, the distance between the generative model density to the joint density of the observations. And there's, again, many ways of doing that, but here we will choose to do so by minimizing the reverse Kullback-Leibler divergence between those two probability measures. And the reason we do so is motivated by the following decomposition. So we can write down the Kullback-Leibler divergence into the two terms you see on the right-hand side. There's an entropy term, and then there's an expectation over the logarithm of Q. And let's see what happens here. The second term can be further decomposed to those two integrals. And then this decomposition reveals an interesting interplay between the entropy term. So what happens if we're trying to minimize the KL divergence? So that corresponds to minimizing the negative entropy, which essentially encourages the support of p theta to spread to infinity. So we're trying to increase the entropy of the generative model distribution. On the other hand, the second integral term is introducing a penalty that penalizes any regions in the probability space in which the support of p theta and the support of q do not overlap. So essentially, that gives us a mechanism that we can stretch the support of p theta as far as we need, but no further than the support of q. And that will be a mechanism that will regularize the training process of this model and will help us safeguard or mitigate the issue of mode collapse that this type of generative models typically suffer from. However, in practice, we cannot really, the entropy term is not tractable in this problem setup. And because we cannot compute it, we'll try to approximate it using a lower bound. And that's what is the derivation that you see there. It's motivated by some information theoretic inequalities. So at the final step, we can derive a variational lower bound for this entropy term, which is bounded by the entropy of the prior, plus some expectation over an additional inference model. This is a variational approximation to the true posterior. You see there Q phi of z given x and y. That essentially introduces this regularization that I just described. Right? Okay, so we have a bound for the entropy, and we still, though, we have to minimize the KL divergence. So how do we do so? In the general case, this is not an easy computation because p theta is an arbitrary density. It's arbitrarily complex. We don't make any assumptions of it being Gaussian or not. Its inputs could be high dimensional, the entries x and y. So now the question is, how can we estimate this KL divergence? And we will do so by a simple trick that's very popular in machine learning these days, and this is density ratio estimation using probabilistic classification. So what you see up there, I'm just repeating the definition of the reverse Kullback-Leibler divergence, which essentially boils down into an expectation over a logarithmic density ratio. And it turns out that we can estimate density ratios using classification. There is a very, very simple proof that you can follow. And essentially, we can estimate the density of two ratios, rho and q, this r of x, by evaluating a classifier, by training a classifier that learns how to discriminate between samples generated from rho of x versus samples generated from q of x. So this is a simple binary classification problem, and that's something that modern tools in deep learning are very successful at. We can build very accurate classifiers even when the inputs are high dimensional, objects like images or time series and so forth. All right? So we will leverage these techniques to get some sensible approximation to the Kullback-Leibler divergence. And essentially, if we do so, we have the tools in place to try to train such generative models from scattered observations of inputs and outputs. So everything boils down into deriving those two loss functions. So we need a discriminator network. That's the network that will try to classify whether samples come from one distribution versus the other. And that discriminator essentially has a binary cross-entropy loss function. And then we have a generator network that is trying to generate samples that look realistic, that look like the training data that we have observed. And then from the derivation that I showed earlier, for the lower bound that we have for the intractable entropy term, we will also have this encoder network that essentially is an approximation to the true posterior over the latent variables. So these are the two loss functions that we need to this defines a minimax problem. So essentially, that's what I call an adversarial optimization problem that we're trying to minimize to recover the optimal parameters for all these neural networks. And this is done by alternating stochastic gradient descent updates between the generator and the discriminator. And what you see here on the right is just a typical behavior of the training process. The red line corresponding to the loss of the generator, the blue line, the loss of the discriminator. And we can also derive and see what is the optimal value for this discriminator. That's sort of like a metric to check whether the training dynamics of the algorithm behave correctly. Any questions so far on the method setup? All right. Okay, so adversarial models, however, they have several advantages, but they have also several caveats. So the advantages is that they allow you to model arbitrarily complex probability distributions. All right, so we can use neural networks and pass samples through them, and essentially at the output space, we can model essentially any probability distribution. They avoid oversimplifying approximations that are usually employed in variational inference, such as the mean field approximations or approximating probabilities with Gaussians and so forth. And therefore, they give you they provide a general platform for building flexible schemes for statistical inference. However, in practice, it's quite hard to train them. The training dynamics can be quite unstable, and they require very careful tuning of the model parameters. And of course, as all variational or inference type of schemes, they don't enjoy the theoretical asymptotic guarantees for convergence that you may get through sampling methods like Markov chain Monte Carlo. So here I'm appending some practical lessons learned. I'm not going to go through them for the sake of time, but essentially they boil down on how can you probably set up this problem and tune the respective networks. Essentially the generator and the discriminator, they have to be balanced in a certain way that they exchange information during model training. But you can find these discussions in the papers that we have, they're on the archive. All right, so let's go and see some examples of these methods, and I'll try to show you examples that are very different from one another. So just to show you some different applications and highlight the broad applicability. So the first thing we can try, the most toy example, would be use these type of models that may look like an overkill to begin with, just to perform regression on noisy data. But we'll try to consider 3 different cases that are inherently different. So the data in each case will be corrupted by some noise process that will be different in nature. So case 1 will have some data in one dimension, a simple one-dimensional function that will be corrupted by uncorrelated Gaussian noise. That will be the standard setup. Case number 2 will be a data set corrupted by heteroscedastic noise. This is a noise process that is correlated in space. So you see their delta, the noise process depends on the inputs x. And then there is the third case that the noise process also appears inside that sine function, and therefore it gives you a case where the noise process is not additive and it's non-Gaussian. And the setup is that we're going to generate randomly 200 data points, pairs of inputs and outputs from these functions. We're going to use fully connected feed-forward architectures for all neural networks, namely the generator, the discriminator, and the encoder. We're going to use a 1:5 ratio for updating those during the stochastic gradient descent update, and that goes back to these caveats I was describing for training adversarial models that require some careful tuning of these relative updates. And then we're going to use an entropic regularization penalty, namely, I think I skipped that part. You see parameter lambda here appearing in the loss of the generator. That is essentially the magnitude of this entropy regularization term that helps us avoid the issue of mode collapse. If we set lambda equals to 1, we obtain a model that resembles a conditional generative adversarial network. We set here lambda equals to 1.5 to introduce some regularization and avoid the issue of mode collapse. And then, since this is a small data set, we will train using the full batch gradient descent with a small learning rate. All right? So here's a summary of the results. So in the left column, you will see the results of this proposed model. I coin it as a conditional generative model. And then we compare against the two standards in the literature, namely Gaussian processes and Bayesian neural networks. So I don't know if the plot is very clear. It seems that it's quite tiny to observe. But the take-home message here is that for all three cases, and regardless the nature of the noise process that corrupts the data, you can get robust results using the conditional generative model and robust uncertainty estimates. Whereas the Gaussian process and Bayesian neural network, they perform very, very well in the case of uncorrelated noise, the homoscedastic case, but they have trouble dealing with the heteroscedastic case. Essentially, they underestimate the predictive uncertainty, and of course, the non-Gaussian and non-additive case. Of course, for the heteroscedastic case, the comparison is not very fair. We could have chosen a particular likelihood model for the Gaussian process or the neural network and account for correlations in the noise process. But that will require a more involved inference procedure. Whereas for the non-Gaussian case, there's not much we can do in the GP or Bayesian neural network domain. But the proposed model does not require any additional modification to accommodate. And that goes back to the form of the observation model. So the latent variables and the inputs could be tangled in a complicated way with one another. All right, so let's see a different example, totally different nature. And this one has to do with the concept of multi-fidelity modeling, which let me explain a little bit first, because I would assume some of you may not be familiar. So the concept of multi-fidelity modeling assumes the following, is based on the following premise. In some cases, we want to approximate some function from data, but the data generating process could be very, very expensive to sample. So we may not have access to many samples. On the other hand, we may not have access to the true data generating process, but we may have access to some simpler approximation. You could think of, you're interested in the target quantity of interest, for which to get an accurate measurement, you need to run an expensive experiment, or you need some expensive, well-calibrated sensors to measure. And that's expensive. You cannot afford many of them. But at the same time, maybe you can buy some cheaper sensors and deploy them in more locations. You will get inaccurate predictions and inaccurate measurements, but maybe you will capture some basic trends. And then your hope is that you can synthesize those two measurements to predict your high-fidelity quantity of interest without without spending too much of your resources on high-fidelity sensors. And essentially, this plot kind of encapsulates that in the context of stochastic processes. You have here two correlated stochastic processes. In this case, the data was generated by sampling two correlated Gaussian processes. And then you get the blue and the red curves are just samples out of this Gaussian process. And let's call the red curve to be the low fidelity process. That's a process that we can easily measure for some reason. Maybe it comes out of a cheaper model, or it corresponds to measurements of cheap sensors that we can deploy. And then the blue curve is a high fidelity process that we don't really have access to. It's quite expensive to measure. Let me give you an example from fluid mechanics. Perhaps you want to measure the velocity fluctuations of a turbulent flow near a wall boundary, right? So you could try to do very high fidelity experiments, or you can run fully resolved turbulent simulations and then probe the velocity at these locations that you're interested. That requires a lot of resources. At the same time, maybe you could try to measure some other quantities, like the pressure, which is correlated to velocity, and perhaps you can measure it more easily by deploying pressure sensors on the wall, all right? And then you will get an auxiliary set of measurements that is not really what you care about, but it's correlated to what you care about. And now the question is, can you figure out what this correlation is, and then use this knowledge to map one result to the other. So this is what sort of you see as a pedagogical example in this plot. And what we're trying to model here, what we're trying to predict, is the statistics, is the conditional density of this high fidelity stochastic process, namely the blue curve, given the input locations, so we have subscripts high and low there. So you assume that the high fidelity data is generated by some nonlinear function of the inputs and the predictions of a low fidelity model and some latent variables. And that induces a conditional probability model over the high fidelity data. All right? So we're trying to infer what this is from scattered observations of the low and the high fidelity process. So namely, what we will assume that we know is we will assume that we have measurements of both processes at these locations, x low equals to x high, and you see the black crosses on the plot. So we have some realizations of both stochastic processes. In this case, we have 50 realizations, and we're just going to measure, we're just going to collect measurements out of these realizations at a finite set of spatial locations. So x equals 0, 0.4, 0.6, and 1. And these are the data that we need to train a model like that, all right? We need these pairs of low and high fidelity observations. Now we're going to use this data and train the model. So during training, the model will try to discover the cross-correlation between these low and high fidelity data. But then during prediction time, where we want to infer things at a new test point, let's call it x star, the process is quite simple. We just have to evaluate the low fidelity model at this point x star. And the assumption is that the low fidelity model is something that we can easily evaluate. Then we're going to record the output of this low fidelity model. And then we're going to push it through this generative model to map this measurement to the corresponding measurement of the high fidelity prediction. So is this clear? And then eventually, if we are successful to do that, we can characterize the statistics of the high fidelity stochastic process for every given spatial location x. All right? So this is sort of the result of this process. If we train a generative model like the one plotted here using the inference algorithm I showed you before, you get a result that you see on the top right. So this is just a visual comparison of the true, the mean and the, we just plot the first two moments, the mean and the two standard deviations of the high fidelity stochastic process. And you see a fairly good agreement based on only those training data points that you see in the black process in the left plot. So now you would say, okay, what does that even mean? Does it even, this multi-fidelity approach, does it even do anything useful? And the answer is yes. The plot that you see in the bottom left is what you would get if you were to train using only the high fidelity data. All right? So you just keep the training points, the observations you had of the high fidelity process, you train a model, and this is the prediction that you get. So of course, this is just to say that incorporating low fidelity data and figuring out the cross correlation between the two can help a lot to actually approximate what you're looking for. And then in the right plot is a more quantitative measurement where we're plotting the forward and the reverse Kullback-Leibler divergence as a function of the spatial location x. For the multi-fidelity case, which is this, the blue and the orange curve that you see that is almost 0, versus a single fidelity model where it has a low Kullback-Leibler divergence at the locations where the high fidelity data was sitting, namely 0, 0.4, 0.6, and 1, but it fails to approximate the statistics of the target stochastic process away from the training data. Any questions? I've confused you enough so far? No. All right. So the next example will be, again, another application of this machinery, but in a totally different setting. We'll try to solve an uncertainty propagation problem through a dynamical system. So namely, we'll consider a conservation law in one space dimension, namely the nonlinear Berger's equation. That is a toy model for modeling fluid flow and traffic flows and so forth. So that's a nonlinear hyperbolic partial differential equation with 0 boundary conditions. And we will try to drive this equation using a random initial condition. All right? And the random initial condition will be generated using a conditional Gaussian process model that you see there. So the initial condition will be a sample from a Gaussian process with some mean function and some covariance function. And this corresponds to a conditional Gaussian process model that is conditioned to satisfy the boundary conditions. All right? So it's conditioned to give you samples that look like what you see in there on the right, where the samples decay to 0 close to the domain boundaries. And then there's some variability in the middle of the domain. All right, so we have this infinite dimensional dynamical system. It's a partial differential equation. We drive it using random initial conditions. So the solution to this problem will be a continuous random field in space-time. and defines an infinite dimensional uncertainty propagation problem. So now our goal will be to construct a conditional generative model for the density P of u being the solution to this differential equation, given t, which is the time coordinate, and a set of latent variables that are there to model uncertainty, where this bold phase u will be a vector in R128. Essentially what we'll do, we'll put a grid on the space dimension of this problem, consisting of 128 grid points. And then our goal is to predict or to model this probability density in this 128 dimensional space, in which each sample from this density corresponds to a solution trajectory of the system at a given time t. All right? So the training data for this problem that we'll consider will include 64 scattered temporal snapshots. So what we'll do is initially we'll try to solve this problem using a conventional PDE solver and just generate some sample trajectories out of the system. And these sample trajectories will be used as training data for the algorithm. And specifically, we will take just randomly choose 64 temporal snapshots out of these trajectories. And then in each temporal snapshot, we will record 100 realizations. All right? So essentially, we have 100 realizations of the system as training data to build this conditional probability model. And then to exploit the gridded spatial structure, because we assume that we will have a space in a grid in space, we will use one-dimensional convolutional neural networks. And then the result that we expect to get out of this analysis will be a conditional generative model that can provide a complete statistical characterization of the random field at any time t, so the user can say, okay, let me see what the solution looks like at time, I don't know, 15.78, and at a finite set of spatial locations that correspond to this 128 grid points that we chose. All right? And this is sort of like a visual comparison of the result. What you see on the left is just the evolution of the system in space-time, and this is the exact samples that are generated using some high-fidelity numerical solver. So what I'm plotting here for each temporal snapshot, I'm plotting several samples, and actually I'm plotting 10 samples out of the exact system. And then on the right, you see the prediction coming out of the generative model that was trained. And this is for test data. So this is for temporal locations that were never seen during model training. So this is sort of like a fresh result. So I don't have like a quantitative measure to show you and convince you that this result is accurate. But yeah, so for this point, we just trust the I norm that you see visually. You get a very good agreement between the prediction and the exact solution. So any questions so far? Because I'm going to switch to a different topic for the rest of the talk. Namely, I will switch to the topic of incorporating physical constraints, because what I've talked about so far was purely data-driven. Someone gives us pairs of inputs and outputs that were generated by a process that was black box to the user. We don't care where they come from. Whereas for the next part of the talk, let's see, how am I doing with time? All right. We will deal with systems that the data generating process has some structure, and we have some prior knowledge for that structure, named in the form of partial differential equations. So essentially, this defines the problem of uncertainty propagation in what I call physical systems that are governed by partial differential equations, in which you have a system that is driven by a set of inputs, deterministic inputs, typically space and time coordinates, x and t, but you also have a set of random inputs that are sampled from some prior distribution P of z. And of course, the dynamics will be deterministic, but because you have random inputs, the outputs will also be random, and now we care about characterizing uncertainty in these outputs by means of constructing a conditional model for what is the solution to the system U, given the spatial location, given time, and the random inputs. All right? And then since we've been talking about similar conditional generative models earlier in the talk, you will expect that what I'm going to show you next is very, very similar, but it will be adapted to the context of, the question we have to answer here: how can we best leverage the knowledge of the PDE equation? We have an evolution law, so how can we use this prior knowledge to improve our predictions? And that brings me to the concept of physics-informed neural networks, which is not a new idea. It might be a catchy term these days, but it's certainly not a new idea. It goes all the way back to work done in the early 90s. At least the first contributions I'm aware of are from Psychologios and Unger and Lagaris in the 90s. And essentially, the question here is, how can we use neural networks to solve differential equations? How can we use neural networks as a representation to the solution of a differential equation, and then construct a numerical method for solving it? And the idea is very simple. So we have some partial differential equation that you see here on the top right. So du dt plus some nonlinear operator acting on the solution u. And like we do in classical numerical analysis, we will assume a representation for the unknown solution. So typically what we do is we assume that it's represented by some linear combination of basis functions. Well, here we're going to assume it's represented by a feed-forward neural network. So and that's what you see here on the left. There's a neural network that takes as inputs x and t and predicts u. So it's a continuous representation. For any x and t, it will give you an output. And it's a differentiable representation. So that means I can take any derivatives that I want with respect to space or time coordinates, which means that I can define this new quantity, which I call up there r of t and x, which is the residual of this equation. So since u is a neural network, I can take its derivative with respect to time and x, and then I can construct this new quantity of interest, r of t and x, which will be a neural network, essentially. It will be a neural network that has exactly the same architecture as u, exactly the same weights and biases, but it will have different activation functions due to the action of the differential operators. All right? So this is essentially what we've done. We represent the unknown solution u with a neural network f theta, so a parametric function parameterized by theta. We can take any derivatives we want of this neural network. That defines another neural network, which I will refer to as a physics-informed neural network, that essentially its activation functions carry some information about the differential operator. And the only difference between the 90s and today is that today we're less patient, I guess, because people in the 90s sat down and derived what those activations were by taking manually all the derivatives. And only that, they derived the backpropagation rule for training this network. In 2019, we're lazy and we're going to use software to do that for us automatically. So we're going to leverage the capabilities of modern software like TensorFlow, and especially the capabilities of automatic differentiation to automatically compute those gradients for us. All right? And if we do have access to machinery like that, then the problem is trivial. We can code this in 10 lines of code. And essentially, we just need to define a loss function that has two components now. So what you see here, this is the equation up there again. The notation's changed a little bit from the previous slide. So now f is the residual to the equation. And then we're going to train the neural network. We'll try to identify the parameters of the neural network representing the solution by minimizing some objective function, which will be a mean square error loss that is comprised by two components. First, you have a mean squared error subscript u, and that is a loss function that is trying to minimize the discrepancy between the neural network predictions and the actual data that you may have. What is the actual data for this problem? Well, it's the initial and boundary conditions for the differential equation. That's something that you know a priori. Or it could be any sort of measurements that you may have inside the domain. The second term in the loss function is a term that's trying to penalize the residual of the equation. So as you see, I defined f to be the residual of the equation. And we'll try to penalize that residual to be equal to 0 at a finite set of, let's call them collocation points. So if you throw away the second term in the loss function, it's essentially you're trying to train a neural network to fit your data, right? But since your data is only initial and boundary conditions, you cannot really hope that training a network on this data will be able to generalize and predict anywhere else in your computational domain. So the second term could be thought of as a regularizer that constrains the outputs of the neural network to approximately satisfy the partial differential equation. And why approximately? Because we cannot really set, during optimization, we'll minimize this residual, but it will never be exactly 0, right? Okay, so let's go to an example. And just to show you how simple things are in terms of coding, consider this one-dimensional example, again, the Berger's equation. In this particular case, we intentionally choose the viscosity parameter to be very, very small, because for this value, this particular differential equation develops, the solution to this equation develops shock-like behaviors and has steep gradients. And the workflow is essentially the next 10 lines that you see on the slide. You define the residual. So you assume that in TensorFlow, U will be a neural network. And then you define another function, f, which is essentially the residual and can be computed by simply taking the gradients of u with respect to x or time and so forth. And you just return the residual. So that's all you need to do to code this. It's literally 20 lines of code in Python. And you can solve PDEs like Navier-Stokes maybe in 50 lines of code in Python. And here's an example, what comes out of this Berger's equation. So again, remember, the data in this case was initial and boundary conditions. These are the black x's. So in this sketch, the horizontal direction represents the time evolution. The vertical axis is space. So what you see here on the far left, these are data that you have for the initial condition. These are scattered points in space. Then the data points you have at the top and at the bottom correspond to the boundary conditions of this equation. And then you can see that now, that if I were to train a neural network only using this data, there wouldn't be much hope that I could predict the solution inside the domain. But now having this physics-informed regularization that's trying to penalize the PD residual, you can recover the solution to this problem everywhere in the domain. Not only that, this problem it's a deceivingly simple problem, because if you try to resolve this using a classical numerical method, you'll soon run into trouble unless you are very, very careful on how you discretize the domain. And this is because of these steep gradients that the solution develops in finite time. All right, so around time t equals 0.5, the solution develops a sharp shock discontinuity at the middle of the domain. All right? And this would be a case, so you see the slider that I have down there between data and models, that would be a case where you have a lot of model prior knowledge, you do know the evolution equation, but you have little data. You only have initial and boundary conditions. And that's just an example to show you how you can utilize this prior knowledge to get a predictive algorithm. I don't have time to show you results on the other extreme, where you have very small modeling knowledge and a lot of data. That would be more related to model discovery. Perhaps you don't exactly know the model, but you have access to a lot of data and you want to identify the dynamics. But there's a lot of work done in the literature, quite interesting work on this front. All right, so, actually here's a result on this case, and that corresponds to the Navier-Stokes equation. So in this particular example, we assume that we don't exactly know the model exactly. We may not know the viscosity of the fluid or some other parameters. But we have some data. We have data, so this is a canonical problem. This is fluid flow past a two-dimensional cylinder at relatively low Reynolds number. And the assumption here is that we have scattered measurements of the velocity field in space and time. This is the two-point clouds that you see here. We measure the u and the v components of the velocity. And now our goal is twofold. We want to estimate the parameters in the equation that we don't know. We want to estimate what the viscosity of the fluid is. But we also want to infer what the pressure is. We don't have any measurements for the pressure, but since velocity and pressure are correlated through the Navier-Stokes equations, we hope that we're able to reconstruct what the pressure is. And indeed it works. You can use a neural network to represent the velocity field for this problem, and then you can use this physics-informed constraint that this velocity field has to satisfy the Navier-Stokes equation, and then out of nowhere, you can obtain a prediction for the pressure field, which if you look at the color bars, the magnitude is different because the pressure in Navier-Stokes is only identifiable up to a constant, but you get a very good qualitative agreement, and in fact, if you subtract the mean field, you get an exact agreement between the exact and the predicted value. All right. And then finally, you can extend this to learn to try to infer things like constitutive laws in PDEs. This is a very simple toy example for a nonlinear diffusion equation where you don't know the diffusion coefficient that depends on the actual solution u, and you can introduce a neural network along with these physical constraints to recover that directly from observations of u. So you can infer what k of u is without having any observations on it. Directly, you just have data, scattered data on u, and for this simple problem, you can recover what k of u looks like. All right, and what I've showed you so far in this physics type informed neural networks, I haven't said anything about uncertainty, and this is the final part, in which we can extend what I showed you in the first part of the talk to actually try to model uncertainty in this type of problems. So essentially, we'll revisit what we saw earlier. We'll try to construct these conditional generative models, P of u given x, t, and z. but this will be constrained such that U satisfies this known differential equation that we know for this problem. And the same machinery applies as before. We can again try to minimize the reverse KL divergence between the joint distribution of the generative model and the observed data. We have the same decomposition. We can arrive to the same lower bounds. And now essentially everything boils down to this final optimization problem that you see, that we have this additional PDE constraint. So we're maximizing the loss of the discriminator, minimizing the loss of the generator, plus a penalty term that's trying to enforce to minimize the PDE residual. All right? And here's just an example of this workflow. Again, the toy problem is the Berger's equation. Again, this will be driven by a noisy, a random initial condition. But now, in contrast to what I showed you earlier, we don't have, this won't be a data-driven approach. We don't have pairs of inputs and outputs that were generated by some simulator. But we'll try to use these physics-informed type of loss functions in order to compensate for this lack of knowledge. So the only thing that we have is data for the initial and the boundary condition. And these are, you see the noisy data for the initial condition on the left, and then the boundary data on the top right. And then in the bottom, in the middle and the bottom panels, you see the model predictions. So you can track the solution, but you also get a sense of the uncertainty, which, as you would hope or as you would expect, it concentrates around the shock development region. All right? Okay. So I think since I'm running out of time and to leave some time for discussion, this is just a summary of what I presented. Essentially, two topics that are interconnected. Both of them had to do on constructing conditional generative models. We saw some applications in regression and multi-fidelity modeling of stochastic processes and some uncertainty propagation in PDE models. The talk was based on methods, so I didn't really show you any realistic applications. So some futures directions definitely include testing the effectiveness of this type of models in applications, considering multi-physics models, thinking of using this type of techniques for nonlinear model reduction, because I sort of bypassed any discussion today on the role of these latent variables, but they give you a pathway for reducing the dimensionality of the problem, and you could think of them as a proxy for building reduced order models. Utilizing the uncertainty estimates that we get out of those models to perform active learning, experimental design, or Bayesian optimization, or any statements about theory which currently does not exist. All right? So to conclude, I would like to thank Nicholas and Daniele for the invitation and the hospitality today. Particular thanks goes to my student at UPenn, Yibo Yang, who pretty much performed all the simulations that you showed today. Some acknowledgement to the funding sources, and I'd be happy to take any questions. Yeah.
So for your 2D flow passage cylinder, what's the Reynolds number?
100.
Okay.
Yeah. It's far from the turbulent laminar. It's a periodic steady state flow. Yeah.
So you mentioned about Gaussian process have a scalability issue, right?
Yeah.
So I'm wondering, is there any way we can incorporate deep learning to maybe overcome the scalability issue of Gaussian process? For example, I'm thinking about if you have some like autoencoder or something like reduced dimension, can we use that reduced latent variable as in the Gaussian process?
Yeah. So there's two. I meant scalability first with respect to the number of training data.
Oh yeah, that's
In
fine.
which exact inference in Gaussian process scales cubically with data.
Right.
But there's been a lot of work on kind of circumventing this issue, right? There's a lot of work in stochastic variation and inference, sparse Gaussian processes, and certain approximations that speed up the inference.
What if the scalability is in the input dimension? Like you have high dimensions, so
Right.
you have to use a lot of data.
So yeah, dimensionality reduction is a promising direction to consider. I wouldn't be too scared of the dimensions of the inputs in the Gaussian process, but especially the dimension of the outputs. If you have multiple and correlated outputs, that's really when the scalability hurts you in this case.
Okay. Thank you.
In several recent papers on black box variational inference, they try to apply transformation to variables, because that's basically do you find that this kind of distribution of variables to be important? Something that you have experienced with else?
So essentially what we're trying to do here is kind of like, I'm not sure I understand the question, but we're trying to model some complex comparability distribution in the physical space, but we want to do computations with something tractable in the latent space. So the latent variables are typically Gaussians, and then we transform those through a linear mapping to kind of approximate complex distributions. And there's many ways of doing this, like approaches like normalizing flows or flow models that people Nicolas are developing. So the question why, I don't think there's a clear answer to what's better. It remains as its name, it's a black box.
So for trading these models based off the reverse KL, how exactly, in your experience, do they compare to, let's say, the Bayesian neural networks or GPs? Do they take? Does this methodology generally take longer? Is it more just like stochastic?
In terms of computational cost, I mean, Gaussian processes, I would say, they're slow when you have large data. This one, in terms of computational cost, is not very expensive. It's just stochastic gradients, right? Like really large data, it's relatively fast. The comparison is more on the robustness and the interpretability, right? Here, I showed you earlier some uncertainty estimates. Well, in Gaussian processes, you can sort of, it's kind of clear. You can say, this is a component of the uncertainty comes out of the noise in the data, but this uncertainty comes, that's the inherent uncertainty of the model itself, because you've seen finite number of training points. In this case, the uncertainty is not really interpreted. I cannot give you a statement of what it really means. So it's the robustness of these uncertainty that's quite different between Bayesian neural network Gaussian processes and this type of process.
Any other questions before we finish? So let us thank our speaker.